I have decided to use this book. There are several books actually. This one is about as good as it gets, just in terms of the flow of the material. I liked it better than some of the others, but if there is any critical material in the other books that is worth including, then I'll include some podcasts. So we already looked at Tony McMichael's book for the evolutionary perspective of climate and health and humans, and we looked at briefly the concept of One Health and planetary health. We will get more into the details in this book in terms of human health in the context of climate change. This is a nice evocative picture. The tagline is from science to practice. So there are uh, epidemiologists and medical doctors who are involved in writing the chapters. And this is a nice book in the sense we have this pollution, and there is a father and a son, or a mother and a son, probably mother and son, walking into this unknown, right? This is kind of what we are facing right now, the future and what it means for health. The book is split into three parts. Our Changing Planet, Emergent Risks for Human Health is part one. In that we have the first chapter on a primer on climate science. Obviously, I have recorded several podcasts on the details of climate science, energy balance, climate change, climate variability, dynamics, and so on. I won't spend too much time on this, but you can always go to my YouTube channel and find lots of podcasts on these things. I included a bit here just to stay consistent with the book in terms of the flow of the material. The main thing about Earth is the energy that comes in from the sun, what we call insolation, and the fact that Earth is a sphere. So since sun is far enough out, the rays are parallel by the time they get to the surface, and there is more energy per unit area at lower latitudes than higher latitudes because of the curvature of the Earth. We have less per unit area. So the depth of the atmosphere the insulation has to pass through to reach the Earth's surface also increases because of the angle it reaches to the Earth. So there is more scatter and absorption. The net result is that all the energy that's coming in is going into warming things, evaporating the water from the ocean, from soils, and energy is being used for various things like photosynthesis. And you have outgoing long wave energy or infrared energy that we cannot see with our bare eyes. That's the energy balance. How much short wave is coming in, how much long wave is going back out to space. It turns out that when you can include all the area considerations, depth of the atmosphere, ice and snow at different latitudes, land use, and so on, you have reflectivity of the surface also being a factor. So some of the incoming shortwave is directly reflected back to space, and whatever is received is then converted into energy. It turns out that there is excess energy when you look at the incoming shortwave and outgoing long wave in the low latitudes, and at high latitudes there is a deficit of energy on the annual time scale where incoming insolation is less than the outgoing long wave. Long wave is being emitted from everywhere, and as Earth rotates, the energy received from the sun on the net is proportional to the area of the sphere's shadow, if you can imagine. If you don't understand, don't worry, you can go and look at the other podcasts on details on energy balance. What else happens when you have energy surplus and energy deficit? If you don't move the energy from the excess place to deficit place, you're going to keep warming the low latitudes and cooling the high latitudes, which obviously doesn't happen. So that means energy is being moved, which is what gives us weather and climate, right? Weather is what you get, whereas climate is typically what you expect. You expect winter to be colder in the mid-latitudes, or in the tropics you expect certain season to be rainier, like the monsoon season, and so on. So climate is a low frequency average. You can think of averaged weather, whereas weather is what you get on a daily basis. And even though sun goes up and sun goes down, sun goes north and south because of the tilt of the earth, weather can change multiple times a day because there are feedbacks in the system: evaporation, condensation, rainfall, winds. Of course, you have cyclones and so on as well, ocean currents, atmospheric winds, and these give us seasonality and weather. So that's the basic of climate science. In terms of energy balance, we can look at it as the unit area of a place on Earth, where if sun is sending us 100 units, there is about 30 units reflected, 23 from the clouds and about 7 from the various types of surfaces on average. So 30% you can think of the energy of the sun being reflected back, or the albedo of the Earth's average albedo is 30% or 0.3, which is what we think about. Which, if everything is reflected, albedo would be 1. When a fraction is reflected, you talk about 30% or 0.3. So the rest of the solar energy is absorbed by the atmosphere, by the clouds, and some makes it to the surface, and then the surface is going to use that energy to do various things, as we said, warming the land, evaporating the ocean, etc. And it's going to emit long wave radiation or infrared radiation. And you can see that even though only 47 is being received by the surface and 23 stays in the atmosphere, so we have about total of 70 units of radiation, but the numbers here are much larger. You have 116 here, 98 here, and so on, because this outgoing long wave energy is being bounced around. Think of yourself under a blanket. Your body heat is being trapped, and that's how we warm ourselves, right? That's what is being done. Why? Because the atmosphere has the so-called greenhouse effect. There are certain molecules which can trap the outgoing long wave. They can allow the incoming short wave to go through, but they are sensitive to the photon at the different wavelength in the long wave radiation frequency and wavelength. So that's what happens. So the outgoing energy is being absorbed by the atmosphere. It's going to warm up, and it's going to send the energy to space as well as back to the surface. So the main thing about greenhouse effect is that the surface is going to be warmer than if you had no atmosphere and all the energy was simply coming to the surface and going out to space. Okay, that's something to remember, because that means if we increase the greenhouse gases, then we are going to increase the energy coming to the surface and we're going to warm. And this is what is happening. But what should happen at the top is, if you have 70 units coming in, then this should add up to 70. So 49 plus 9 plus 12 is 70. Okay, so that's how the energy balance works. We are rushing through it because, as I said, in this book we are just getting a primer on climate, and a small part of that is energy balance. But also I have detailed podcasts in other courses you can look up, and there are lots and lots of details here, of course, about latent heat, sensible heat. So evaporation, condensation is the latent heat. It's not directly visible, and sensible heat is the temperature difference between the surface and the atmosphere, for example, which is taken up by the rising air currents, whereas here water vapor changes to liquid and ice to pick up the energy during evaporation and release it in the atmosphere, either locally or far away somewhere else. Okay, that's the story. Maybe I should leave this introduction here and come to the greenhouse effect in a bit of more detail in the next podcast. Okay, so just remember: sphere, incoming solar, outgoing long wave, excess energy in the low latitudes, deficit energy in the high latitudes, and energy balance requires that we move energy from excess to deficit regions, and the outgoing long wave balance the net incoming short wave, including the greenhouse effect. So greenhouse effects trap some of the outgoing long wave and warm the surface. That's the basic idea about greenhouse effect, and that's what is given a balmy temperature on Earth compared to Mars or Venus, where there is a runaway warming on Venus with 460 degrees centigrade on the surface. There's a runaway cooling on Mars with minus 50 degrees centigrade, right? So this presumably is what has also led to evolution of life on Earth, even though we don't know whether there are some life forms living on the other planets as well. So we'll come back and look at some more details on the greenhouse effect and what humans are doing to the greenhouse effect by burning fossil fuel, changing land, and so on and so forth.